Hi, my name is Kassandra Avila, and I am with the Department of Science and Engineering at Texas Christian University. And this summer, with TAMU's O-REU program, I worked with machine learning to design optical components. I'd like to thank my collaborators, Shufeng Lan and Kaushik Katarkar, along with my sponsors, TAMU, O-REU, and CREDS. This work was supported by the Department of Energy National Nuclear Security Administration under award number DENA 0003857. In the manufacturing of optics, engineers need to satisfy a set of requirements needed to develop lenses. The purpose of this research is to make that decision-making process easier for the engineers by developing an algorithm that will produce a design based on input requirements. This is possible with the incorporation of machine learning. I was introduced to machine learning and its coding concepts through Jupyter Notebooks. Additional tutorials equip me with the knowledge to navigate information in the material science realm and apply it in Python. Some lessons covered in the tutorials included querying databases, neural network regressions, and among many other concepts that I will discuss later. Before I get into it and explain an application of machine learning, I must introduce the concept of resonance. Thinking of a swinging analogy, when swinging someone, it is important that you match the natural frequency of the swing when you apply your pushing force. This is displayed on the left. Now, if you go against the frequency, you risk getting hit by that person as they are in the middle of their swing, which is displayed on the right. This will not only knock you down, but reduce the amplitude that the swinger is reaching and therefore cause them to swing lower or slower. In order to make that swinger go higher, you must push at the moment they are at their peak amplitude so that they will swing higher and higher. That is resonance. In optics, resonators can be used to store photonic energy. The performance of a resonator can be measured by its quality factor, or Q factor, which is the ratio of the initial energy stored in the resonator to the energy lost in one radian of the cycle of oscillation. The figure on the left shows a photonic crystal slab made of silicon nitride that was subjected to a beam of light and tested to generate spectra with photoresonances. The graphs on the right show the results of the tests using three different methods. Now, as you see there, the TE1, TM1, TM2, and TM3 are the measured transverse magnetic and transverse electric bands. The first graph, the top red one there, displays the results of the ground truth method, which was numerically calculated. The third graph, the green one on the bottom, displays the results of the end-to-end deep learning approach. These previous approaches are unable to provide accurate predictions for ultra-high Q-factor resonances. They are also limited in their process due to their long calculation time ranging from several hours to several weeks. The middle graph displays the results of the spectrum predicted by the RIDL strategy. The RIDL strategy can accurately predict high Q-factor resonances in a reduced amount of time, along with less training datasets, which is 10% compared to previous methods. To produce accurate ultra-high Q-factor resonance predictions and obtain the ability to perform inverse design, the resonance-informed deep learning strategy can be implemented. This diagram will help with the understanding of how the coding works, and we'll start on the left. With forward prediction, first we start with a physical resonance. With the RIDL strategy, this can be applied to Fano, Lorentz, or Gaussian resonances. This makes its first stop at the decomposer. This is where a spectra is decomposed with an adaptive data acquisition method. This method uses training data to describe spectra with resonances using a small amount of data points. It then extracts a set of analytical parameters. Now, using these parameters and their associated resonance field information, The resonance is then classified into its properties to then follow its designed regression neural network. This is where the resulting predicted resonance will be generated. This predicted resonance is then combined into predicted spectra with other resonances. And now, inversely, because the algorithm is able to predict resonances in a timely manner, it has better capabilities to perform inverse design. This means it can work backwards to design slabs that satisfy multiple input constraints. This R-ideal strategy was implemented by my collaborators, along with their colleagues, in COMSOL multiphysics software with MATLAB. The resulting code produced an inverse design algorithm that generated slabs that satisfied multiple input constraints, as described in the previous slide. The machine uses data from multiple resources and creates an algorithm off the trends it detects. Using the input data, the machine can be used for a variety of desired results. Now, for example, a machine design engineer could simulate a structure they wanted to create, and the machine would be able to provide their exact design and tell the engineer any faults or specific results they wanted from the study. The amount of time it takes is lower in terms of man hours, and it will also vary depending on the size of the input data sets for specific tests. The result of the machine learning is that you end with the highest output with the addition of proof in the simulation results. You can simulate an exact design that you need, and the machine can tell you in time if it will work or not. In this research, I gained experience in the coding of machine learning strategies, along with hands-on experience with Jupyter notebooks and COMSOL software with MATLAB. Thank you.